Now that we have created our mesh, let's move in setting up the physics for this project. We can do that by clicking on Setup, which will open Fluent. Though before Fluent opens up, we are asked to specify a few settings from the Fluent launcher. We will enable double precision. And this is generally a good setting to use because it can make the solution more accurate. Another setting to define that can be very helpful is the processing options. When serial is chosen, only one core is used to solve the solution, and this is likely the best choice for small models. On the other hand, when we choose parallel, multiple cores are used, and this is typically the best option for large models, as it splits the tasks to multiple cores running in parallel. So our 3D mesh has a lot of cells, so the solution should solve faster with a greater number of cores. I found the solving speed to increase linearly with the number of cores, so using 8 cores, for example, is about 8 times faster than using 1 core. My processor is a dual core, so I will choose to use both these cores by inputting 2 for processes. Note that you will need a special HPC license, or high performance computing license, to use more than 4 cores. And now let's click OK. All the different settings in the solution setup are simply affecting the mathematical model, which are the governing equations and the boundary conditions. So that's really the only thing we're doing here. First, let's go in General. And the default settings here are fine, so we don't need to change anything. This is a steady simulation using the pressure-based solver. Now under Models, we will edit the Viscous settings. So click on Viscous and click Edit. And we're going to change it to K omega. We will use the SST model. So you can enable this here. We won't change the other settings, so you can just click OK. Under Materials, you'll see that we just really have a catalog of materials. We see that air is already present by default. Let's look at its properties by clicking on Air and then clicking on Create Edit. You'll see that the density and viscosity values are the same as in the problem statement. So no need to edit anything here. Next, let's go in Cell Zone Conditions and click Edit. So the first thing to notice is that this is where you define which material you will use for the simulation out of the material catalog. We see that air was already chosen by default. If we click Edit, we can see that the properties that will be used, and these are simply the rho and the mu that will be used in the Navier-Stokes equations. Okay, next we will tell Fluent to perform our simulation in the rotated frame of reference that we talked about in the pre-analysis section of the tutorial, and we will do that by enabling frame motion, and then we'll input the blade rotational velocity to be negative 2.22 radians per second. Notice that this rotation is defined to be about the positive z axis, as shown by the one right here.